Welcome back. Today we will be discussing about sensor interfacing and signal conditioning. Let's begin with sensors. What exactly are sensors? We have discussed it before also. Sensors, or sometimes we call them transducers. These actually convert physical data like temperature, pressure, ambient light intensity, speed to electrical signals. The most common sensors, these transducers, they may produce an output. That is electrical in nature, but it can be anything. It can be in the form of voltage change. It can also be in the form of current change. It can be in the form of capacitance change. It can be in the form of resistance change. Anything. However, when interfacing with microcontrollers, we need to convert these signals to voltage changes only. In order to send it to ADC, analog to digital converter, and ADC will subsequently send it to microcontroller for processing. So from sensors we get from transducers we get electrical signals. They convert the change in temperature or change in pressure or any other physical quantity to electrical signals, and these changes may be in terms of voltage, in terms of current, in terms of capacitance, in terms of resistance. And then we have a signal conditioning block that conditions the signal so that it may suit our ADC or it may suit our microcontroller. That is, all the changes are converted to voltage changes only, and then the signal is fed to ADC. ADC converts analog signal into digital signal, and then it's fed to microcontrollers. This conversion from voltage change, current change, capacitance or resistance or any other change to only voltage change is known as signal conditioning. It can be simply resistance to voltage change, current to voltage change, or it may also be voltage to voltage change, for example amplification. Whatever output we are getting from the transducer, it may be very small in nature, maybe in millivolts, in microvolts. So before giving it to ADC for processing, we need to amplify it. That also comes under signal conditioning. So we may have something like this. We may have analog signals. We have analog world here. And here we have maybe temperature, maybe pressure, or maybe something else, light intensity. These are taken as an input by a transducer. And at the output of the transducer, we get something like this, maybe some voltage, maybe some current, or maybe some resistance. And then usually we have a block what we call as signal conditioning. And at the out of this signal condition, it gives a voltage, but this voltage may be analog in nature. So this voltage is given to an analog to digital converter, and then the output of ADC is given to microcontroller. most of the modern microcontrollers like Atmega 328, most of the microcontrollers we use today in actual projects in day-to-day life, they have an inbuilt ADC. So then this whole block becomes one, and this is microcontroller. But in case of 8051, we don't have any inbuilt ADC. So whenever we need to interface a sensor with microcontroller, we need to incorporate an ADC in between the transducer and ADC apart from signal conditioning block. Let me try to explain how we exactly interface sensors with our microcontrollers, or what exactly is actually a signal conditioning block. Let me take example of a very basic sensor. I might have a picture here. This sensor is known as thermistor. It is actually a resistor, or I may call it a variable resistor, whose resistance changes by the change of temperature. Resistance changes by increasing or decreasing the temperature. So its output resistance, the output resistance here, is actually a function of temperature. So this is a sensor. What does this sensor do? It converts a physical quantity, that's a temperature, into an electrical quantity, that is change in resistance. Similarly, we have another sensor that is known as LDR, light dependent resistor. Or we also call it a photoresistor. Let me show the picture. This is a photoresistor. What happens? It is also a variable resistor. That is, resistance between these two legs of an LDR is variable, and this time the resistance changes with the change in the intensity of light. That means the resistance will either increase or decrease depending upon how much light is present, how much ambient light is present. These temperature sensors, they are usually of two types, NTC and PTC, negative temperature coefficient thermistors and positive temperature coefficient thermistor. What you are seeing here in the diagram is a negative temperature coefficient thermistor. What's a negative temperature coefficient thermistor? Its resistance decreases with increasing temperature. For example, the one you are seeing in a diagram may have a temperature resistance profile something like this. At 0 degrees Celsius, this is temperature in degrees Celsius, and this is the output resistance, is approximately in kilo ohms, is 30 kilo ohms. When we increase the temperature to 25 degrees Celsius, the resistance drops to 10 kilo ohms. When we increase the temperature further to 50 degrees Celsius, the resistance output resistance decreases to 3.9 kilo ohms. When we further increase the temperature to 75 and 100 degrees Celsius, the output resistance only remains 1.7 kilo ohms and 0.8 kilo ohms respectively. So as you can see, a thermistor actually responds to the temperature change by changing the resistance. So how do we convert this resistance change into voltage change? That voltage change should be recognizable by our ADC. This actually is called as signal conditioning. I will show a simple electrical circuit that will actually change this resistance change into voltage change. The electrical symbol for a thermistor is something like this. This is thermistor. And similarly for a LDR, light dependent resistor, or we call it a photoresistor, it is electrical symbol is something like this. It also has two terminals, thermistor, and LDR also has two terminals. Or sometimes we also show it like this. LDR. So let me show now how we change this resistance change into voltage change. We will insert it in a circuit like this. We have a constant voltage source. We have a constant voltage source V, and then we connect one end of this voltage source to a fixed resistor. In series we connect our maybe thermistor or LDR. The other end goes to the negative of the voltage source. The voltage at this point will actually be the voltage across the thermistor, VTH. VTH. This is our thermistor, and this is a fixed resistor, maybe of 30 kilo ohms. And the value of this resistor, this thermistor, it changes with increasing temperature. It changes from 30 kilo ohms to 0.8 kilo ohms. So maybe this fixed voltage is equal to 9 volts. So when the temperature is very low, when the temperature is 0 degrees Celsius, what will be the general formula of the voltage at this point, the voltage across thermistor? It will be something like this: VTH equal to total voltage V, that's 9, multiplied by RTH, resistance of the thermistor, divided by total resistance, that means 30 plus RTH. Of course, since the resistance was in kilo ohms, or let's assume that the resistance was only in ohms. This resistance is only in ohms. We have a thermistor whose resistance changes like this. At 0 degrees Celsius, the resistance is 30 ohms, and then it decreases up to 0.8 ohms. So we have a and then this resistance will also be only 30 ohms. So now we are calculating the voltage here. When the temperature will be 0 degrees Celsius, the output VTH, since at that time RTH will be 30 ohms, that means VTH equal to 9 into 30 divided by 30 plus 30, 60. That means 4.5 volts. And when the temperature rises to maybe 25 degrees Celsius, RTH at that time is only equal to 10 ohms. So VTH equal to 9 into 10 divided by 10 plus 30, 40, equal to something equal 9 divided by 4 equal to 2 point something. Similarly, when the temperature reaches to maybe 100 degrees Celsius, RTH will be only 0.8 ohms. So VTH equal to 9 into 0.8 divided by 40 plus 0.30 plus 0.8. So it will be approximately 7 divided by 30. That will be 0.02 approximately. Or 0.2 only. So as you see now, with increasing temperature from 0 degrees Celsius to 100 degrees Celsius, the voltage is decreasing. So we have converted the temperature change into voltage change. Our transducer was only changing this temperature change into resistance change, but we have found a way to change this resistance change into voltage change. This is known as signal conditioning, and this VTH we can feed to an ADC, and that ADC can convert this analog voltage that changed from 4.5 volts to 0.2 volts to a digital signal. And then we can feed that to microcontroller.